Hi, everybody. Okay, so today I'd like to go over the conservation of energy and momentum in a collision lab worksheet and kind of what you got to do for it. Okay, so just to review what the lab actually is, the question that we're trying to answer is we're trying to show that energy and momentum are conserved through an experiment. And this experiment includes an air track, and there's two carts on the air track. And we're colliding the carts together and seeing how the energy before the collision, how that compares to the energy after the collision. Uh, so one cart will be at rest, and the other cart will be moving with a certain velocity. And when they hit each other, so when the moving cart hits the stationary cart, we're gonna investigate what happens. So again, we do this with the air track and the ultrasonic sensors. Okay, so let's start with the theory portion. So what type of energy is being considered in this experiment? So for this question, you should consider what are the different types of energy and use that information to answer this question. Um, right. Okay, so for number two, um, what does it mean for a collision to be elastic? So uh, here's a video of a inelastic collision by Tojo.
Run it and make it.
So I think that this video is an inelastic collision because the pumpkin loses all of its velocity in the collision. So if this is an inelastic collision and an elastic collision is the opposite of this, you can use that information to figure out number two. Okay, so for number three, I think that this information is in the lab manual, so I suggest reading through the chapter 11, the corresponding chapter to this lab, and you can actually get the equations for number 3, 4, 5, and 6. So you can figure out all of these from the lab manual. Okay, so for number 7, okay, what function do we use to find the theoretical TE value? And so this question is really asking, what is the equation for the transfer of energy ratio? And there are actually two different equations that we can use for the transfer of energy ratio. Both are the theoretical equations, but one of them includes velocity and one does not. So number 7 is asking for the equation that does not include velocity. So it's the equation that's only in terms of the masses, I think. Okay, so next, so yeah, that's in the lab manual as well. Number 8, what equation do we use to calculate the TE ratio in this experiment? So this one is actually asking which of the equations, so remember there's two equations that we can use to get the TE, and which of these two equations are we plugging our data into? That's what this question is asking. So we're going to use that the numbers in the spreadsheet to plug it into one of these equations for TE, and we're going to use this equation to calculate our experimental TE value. And so it's so you have two choices for TE. There's two equations for TE, and you can see that number 7 says that number 7 is asking for the equation that is independent of velocity. So number 8 will refer to the by process of elimination. Number 8 will refer to the other equation. So there's two equations for TE. One of them includes only mass, the other includes some other stuff. So yeah, so pick which one you think is right for the answer for 7 and 8. All right, next let's move on to the data analysis. So it says fill in the following data tables. Remember to discard points with S is greater than 0.5 meters. Making your plot. So up here, S refers to the distance of the cart from the sensor. And yeah, so again, I will show the data. And what I want to see. Great. So the tables you're going to fill in using this data. And one thing to note is that you see these velocity columns. They're asking for velocity here. You're actually going to want to include your uncertainty in the velocity column. So it's going to be something that might look like um, 1, 2, 3 plus or minus 4, 5, 6. Right. So I just use these random numbers, but you're gonna want your like your average value plus or minus your uncertainty, like so. And if you're confused on what uncertainty is, I recommend reviewing the lab manual chapters. I think it's chapter 5, 4 and 5, I think, or whichever ones are related to this uncertainty error and the way that you calculate these things. Okay, so clear that. All right. So, but how do we actually calculate these V1I, V2F thingies? So again, these are referring to the velocities and the subscripts. So V1I refers to cart 1 initial. So this is velocity of cart 1 in the beginning. And this V2F is referring to velocity of cart 2 final. So after the collision. So this is velocity of cart 1 before the collision, velocity of cart 2 after the collision, and your TE ratio, which you can use your equation to find. So this will be your experimental TE ratio. So this is the equation that includes the velocities. So you're going to use these two columns to get this one, but how do you get these two? Okay, so to get V1I, let's start with that. So this first column, you're first going to have to convert the data to the S, so the distance from the sensor. Distance of the cart from the sensor. So this is very similar to what we did in the previous inclined plane lab, where you went from data that looked like data that looks like this. So you went from data that looks like this, right, with the timestamp and the delta t's. You went from that to S using this formula. So let me write the formula on the left. Right. So this is the formula that you use to get the S's from the delta T's. And in this case, you're actually going to want to use 343 meters per second for your VS. So right, so you need this speed of sound to calculate the distance from the sensor of the cart. And you did calculate this in your other inclined plane lab, so it's okay if you want to use that value that you calculated last time, as long as it's close to 343. But I suggest if you got like some weird value, that you use this 343 meters per second. All right, so this is how you do the first step in getting this V1I, right? So this is what we're trying to get, V1I. The first step is to convert your delta T's here, convert these delta T's into the S using this formula. So for every delta T, you're going to have a corresponding S distance value. All right, so once you have that, you're going to actually want to graph something. So you're gonna actually graph your S values against time. So you're gonna get so this is step one. Step two is okay, don't call it that, but think of a better name. And this is step two. So once you get the S's, you're actually going to want to graph your S values in accordance to their T values. So I can get this back. So you're going to get like an S for every row, and you're going to have a corresponding timestamp. So it's little t. So you're going to graph your little t on the x-axis, and your S, when you get it, you're going to put it on the y-axis, and you're going to get a graph. So your graph is probably going to look like this or something. And then you're gonna fit a linear fit to that using Davis, as always. And once you fit your linear fit, it's gonna output a slope. So you're gonna get like a maybe I won't call it. I think they call it A equals so minus meters per second, right? So this is the number you get from Davis, and this is, as you might remember, slope is your rise over run. So your change in your y, your S divided by your change in your time. And this is actually the definition of velocity. So the slope of this graph that you create is going to be your velocity, right? So that's how you get this this V1I, this V1I value right here. This will be the slope of your graph, including the uncertainty. Oh, sorry, that should be centimeters per second. Wait, should this be? Okay, so I think that you have to convert your velocity to centimeters per second in the end. So so whatever you get for your slope, because you use the speed of sound in meters per second, your slope is going to be, the velocity you find is going to be in meters per second. So just because they're asking for centimeters per second here, you're going to have to divide by 100. So or no, multiply by 100. So whatever you get, you're gonna multiply that slope by 100 to get your stuff in centimeters per second. Okay, so that's how you do that. Yeah. Yeah, to get the TE ratio, you should use the equation in the lab manual and plug in these two things. So, okay, so for the final TE values down here, it says what is the final TE value? For these, you're gonna want to actually you're just gonna want to average over your 4 trials. So average over these four numbers. And when they ask for this uncertainty, they're just asking for the standard deviation of the mean of these 4 numbers. So that's what you'll get for your uncertainty. So you're going to get 4 numbers here, and you're going to average these numbers, and your uncertainty will be the standard deviation of the mean of these 4 numbers. All right, so that's how you do that. And conclusion. All right, so it's asking again for this confidence and the agreement. So I suggest you review the lab manual on how to do these calculations, because these are both numbers. And what else? I would like to see that you write what these numbers mean. So once you get a value for your confidence and a value for your agreement, if you could put a sentence saying what this value means, and that would be nice. Okay. I think the virtual experiment is if you follow the instructions, I think it should be okay. And that's it for the worksheet. Thanks for watching.